welcome. I'm Bob Young, Assistant Professor of Mathematics at Brevard Community College. With the help of my fantastic behind-the-scenes support staff of WBCC, we have developed a new series of lessons entitled Empowering Introductory Algebra. The series was created and has in mind students who have struggled with algebra in the past and for returning students who need a basic skills algebra review. Our wish is to provide you, the student, with the algebra fundamentals necessary to become successful upon entering those college-level courses, even if you have never had any success in any mathematics course. Now, where we're going to begin our adventure is discussing algebraic expressions. We're going to express ourselves algebraically. So let's go to our first graphic here, and we're going to look at some definitions and so forth. A variable represents a number. It may change or remain constant. For example, the variable A may represent your age, which changes from year to year. Or B could represent your birthday, which remains constant. In the next graphic, an algebraic expression consists of variables, numbers, and operation signs. Oftentimes, the expression is some combination of these. To demonstrate how two items are combined in algebra, let's use the variable x and the number 77. So, for example, to show addition, we write x plus 77 or 77 plus x, has the same meaning. Sometimes they even put parentheses and quantify parts, so you can use parentheses with addition as well, and notice you can write it in reverse order. Now, to show subtraction, we write x minus 77, or with parentheses, x subtract 77. Now, notice you cannot write subtraction in reverse order. It does not have the same meaning. So, in other words, x minus 77, 77 minus x, not the same creature. Now, multiplication, it can be shown in all kinds of varieties of ways. Sometimes you see algebra textbooks use the dot to show multiplication, 77 times x with the dot. Sometimes you just have plain old parentheses with no signs between them, so if you don't see any addition or subtraction signs, just plain parentheses back to back means multiply two things. And then they go crazy sometimes and have both parentheses and the dot to show multiplication. But the easiest way I like, my best way, is just to put the number in front and then the x. So 77x, I feel, is the best way to write multiplication. It's the easiest. Now notice on the bottom down there, x77 is not very good syntax in algebra. It really does mean the same thing as 77x, but usually they always put the number first. And notice the old-fashioned way to write multiplication, 77 times x. If you use the old symbol times, it's kind of frowned upon because you could mean multiplying by two x's there, so be careful. And in the next graphic here, before we go to some examples, division can be expressed the old-fashioned way, but is usually expressed in fractional form. So x divided by 77, sometimes they'll even put parentheses on the items and put the division symbol between. But most often in algebra, they write division using fractional form. All right, so let's go to some examples, and we will demonstrate some of these concepts. So first thing we want to talk about is evaluating algebraic expressions. When replacing a number for a variable, we use what's called substitution. So some examples here, it says evaluate 8y when y equals 7. So what we're going to do, what does 8y mean? Well, it means take 8 and multiply it by that number y we're substituting in here. So really all this is saying is 8 times 7 is 56. Now remember, this 8y could have also been written 8 times y with the dot. It could have been written with parentheses. It just depends on the textbook and the problem. Okay, so evaluate number 2 example here, m plus n over 2. Now over 2, this is one big what here? Division bar. So we're going to go ahead and plug these numbers in first. So we're going to take where we see an m and put in a 12, where we see an n put in a 4, and then we'll go ahead and evaluate this algebraic expression. All right, so first we say 12 plus 4 is what? 16 divided by 2, which gives us the answer of 8. All right. Now, let me talk to y'all for a second here. A lot of people say, when am I ever going to use this, Young? I'm learning this algebra, these variables and substitution, evaluation things. When am I ever going to use this in real life? I'll never use this stuff. Oh, I think you will. Let's go to our next example and we'll show you why. All right. Now, this is a formula your banker loves to use. If you go to buy a house or if you go to buy a car, and what it says is interest equals principal times rate times time. So I'm great at spending other people's money here. I'm going to go ahead and we're going to buy a house today on our first episode. And I'm going to go ahead and let our house be, an $80,000 house. So we're going to go to Mr. Banker here, and we're going to borrow $80,000 to build a new home here in the area. Now, the going rate, I would say, is probably about 7%. So if we multiply here, we're going to multiply by 0.07. Remember, you can't multiply by a percent. You have to change it to a decimal. And the time you usually finance a house is what, about 30 years? So we'll finance this $80,000 home at 7% rate for 30 years. All right, so let's go ahead and multiply the numbers now. So I'm going to go ahead and multiply the 80,000 times 30 here, and I'm just going to take 8 times 3 and make that 24, and then put the number of zeros. 1, 2, 3, 4, 5. Let me make sure I got that. 4, 5. 2, 3, 4, 5. And then I'm going to multiply by that 0.07 here. All right, so that'll be 0, 0, 0, watch me out there, 0, 0, 28, 2, 7 times 2 is 14, 16, and then when we multiply decimals, we move it over 2 places, so this would end up 2 places here, and I'll go ahead and put my comma. So the interest, using this banker formula here, y'all think evaluating algebraic expressions never applies to you out there. Oh, but it does. Check this out. We get the interest on this home is $168,000. $168,000. But that's not even how much our home cost after 30 years. We have to go down and evaluate this algebraic expression in order to figure that out. So how much did we borrow in the first place? This formula here, or this equation, says the amount that you pay everything back equals how much you borrowed plus the interest. All right, so we started out with what, an $80,000 home, and then the interest was $168,000. So if I line that 80 up under here, let's see how much our home cost. Our $80,000 home, how much it cost at the end of 30 years. Check this figure out. Woo! So people out there say we never use these algebraic expressions, or we never use algebra in real life, but boy, look when you go to buy a home, folks. And for you young people out there, think about this formula with a new car. I mean, you could put in principal 20,000, the rate, I mean, for a new car might be 6 to 10%, time 4, 5, 6 years. And boy, I mean, I've even seen some car dealers go as far as 8 years on this. So, I mean, it does certainly affect you down the line here. Okay, so the next thing I want to look at, let's go back to some graphics. All right, translating algebraic expressions. A lot of students have trouble when it comes to word problems or translations because they don't know the meaning of some key words. So for addition, for example, here are all the words that I've seen in algebra books, and I'm sure there's others out there, but these are the ones used most for addition, and you can go ahead and make notes of these here as we go through. Addition, sum, total, greater, plus, in excess, increase by, more than, all together are all words that mean to add. All right, in our next graphic, words that mean to subtract, subtraction, minus, difference is a huge one here. A lot of students, when they see the word difference, they don't know that means to subtract. Takeaway, with football season coming up, boy, you want your team to win that giveaway takeaway battle at the line of scrimmage, or you want to take that ball away when possible. Decreased by, diminished, subtracted from, and less. Now you notice the asterisks on those last two. Whatever comes first is written last. And an example down there, 5 less than x is written x minus 5. And boy, that little word less is used a lot to show subtraction in algebra. 4 subtracted from y is written y minus 4. When if it would have just said 4 subtract y, it would have been 4 minus y. So boy, you really have to watch some of these words as you translate algebraic expressions. The next operator in math we want to talk about, multiplication and division. So here's some key words there to get down as we go through. Multiplication, product, times, of. Usually they use the word of to show multiplication when there's a fraction involved, like 1/2 of some number would show multiply by that. Twice, doubled, tripled for you baseball fans out there. Sometimes if you hit a double, that means times 2, tripled times 3, and so forth. Division, you have division divided by quotient is a word often not understood to mean division by students coming in. It's been out for a while. Half, per, and into. So let's go ahead next and look at some examples translating algebraic expressions. So we'll see if you understand the meaning of some of these key words. So for example, example 1 here, the sum of 5 and y. How would I write that? Well, you could write 5 plus y, knowing that this key word sum means to add. Or also, if you think about it, putting numbers in for y, you could write y plus 5. Has the same meaning. So a couple different ways to write addition. 17 less than a number d. Now there's that little word less, and that's the one that's dangerous. It had the little asterisk there on that graphic, so watch out for whatever comes first is written last. So this would be d subtract 17 or d minus 17. Okay. 12 more than b. What does that mean, Young? Well, the word more than, if you were paying attention earlier on, means add as well. It's another word like sum here, so we'll say that is 12 plus b, or you could write that as b plus 12. Now notice up in example 2, you cannot write the difference of something in reverse order. That would not be the same number if you plugged in. All right, let's look at a few more here. More examples. We like to give you lots of examples here on the WBCC network so you can go to class strong and feeling the power. That's why we named this episode of series the Empowering Introductory Algebra. All right, so now the quotient of 12 and c. See, now if you came in and didn't know what that word quotient meant, you would have been a little bit lost here. Now remember, there's a few ways to write division we've discussed already. 1, 12 divided by c. You could write the quotient that way. Or you could write in fractional form 12 divided by c this way. I would say the fractional form is the more accepted way of writing algebraic expressions in algebra here. So we're just moving right along here. We like to give you lots of examples, so when you get to class, you're going to know what's happening. The product of x and 9. Product meaning what? Multiply. So we're going to take these numbers and multiply. You can, lots of ways to write multiplication. Put 9 dot x, you'll see. You might see parentheses, 9 times x written that way. Or the easiest way, the lazy person's way, and that's what I like the best, is just plain old 9x to show multiplication or the product of something. The sum of a and b, we've seen this again. So sometimes they will mix just plain old variables in, means to add. A plus b, b plus a, does not matter here. And lastly but not leastly here, as we continue our adventure, we've got the difference of y and 20. Difference is a key word meaning what? Right, subtract. So watch the meaning of those key words. It will just make you strong translation-wise here. So this will be y minus 20. Now could we write that in reverse? Survey said, no. All right, 2/3 of p. Of's that little word meaning what? Multiplication. The easiest way to write multiplication here would be 2/3 p. 2/3 p on that one. All righty, so going back now to the graphics, boy, we've just got all kinds of things to show you here in our episodes. We've got examples, graphics here, all kinds of good stuff for you to get in your notes. Let's talk about the set of real numbers. These are the numbers we use most in algebra that make up our number line. All right, so when we start out talking about real numbers, I like to talk about the little curly-Q things, which represents a set of objects. So whenever you see those little curly-Qs on something, it represents a set. And again, they usually call sets by capital letters. So for example, moving down there, it says the set of numbers A may be written A equals, and they got the little curly Q lines there, 0, 1, 2, 3, 4, 5. So that would be the set of numbers A. And then that little symbol there means subset. So when you see a symbol like that between sets, it says, for example, the set of numbers 1 and 2 would be a subset of set A, or the set of numbers 0, 1, 2, 3, 4, 5. It's in there. It's in there. All right, moving along on the next graphic, the numbers the caveman started with. Let me come up here and look at the audience here. When dinosaurs roamed the earth in prehistoric times, what did man begin counting on? You know it, UG 1, UG 2, UG 3, and so forth. And when he ran out of fingers, he went to what? Well, like me, he went to his toes there. That is called the set of natural or counting numbers. All right, so I'm going to go to some examples here. I made up a little number line for you here. The set of real numbers that make up our number line. So when the caveman started counting, 1, 2, 3, 4. And you could keep on going forever and ever. That's what the arrow means. You could go 5, 10, 100, 1,000, 1,000,000, some professional athlete salaries way on out there. All right? And when you add 0 to the mix, you get the set of whole numbers. All right? So 0 in the mix gives you whole numbers. Now, what are we missing on our number lines? Well, we're missing the set of numbers called integers. So let me just go back to that graphic here real quick. I'll keep my film guys on their toes. Notice we have the natural or counting numbers in that nice set notation. 1, 2, 3, 4, 5, 6, dot, 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 means keeps on going out there. Whole numbers got the 0. And the integers, a lot of students think like -2/3 is an integer when it's not. See, integers don't contain any fractions or decimals. They are just either negative counting numbers, positive counting numbers, or 0. All right, so let me go back to my example here. Let's go ahead and fill in the integers on the number line. All right, so when it was time to pay taxes, we needed some numbers over here, didn't we? That's a bad one there, taxes. Oh, my gracious. All right, -1, -2, -3, on out. And the larger the negative, the smaller its value here. So there are the numbers on our number line. We've got the natural numbers, whole numbers, all of these integers, but we're still missing numbers here. What kind of numbers are we missing on the number line, Young? Well, let's look at this next graphic here, and we will show you. We are missing rational numbers. Now, whenever you see the word rational in algebra, I want you to think fractional. Rational numbers represent fractions or decimals. Now, the decimals must terminate, which means end, or repeat. So any decimal that terminates or ends, or a number that can be made into a fraction, okay, that's a ratio of something A over B, where A over B are integers, and of course B can't be 0, we'll talk about that later on, are called rational numbers. So let's put some of those on our number line here, and let's go back. So I'm going to go ahead and pick the fraction -1/2 and put it on the number line. Now, what decimal is that? Well, to make a fraction into a decimal, you always take and divide the bottom number into the top number. All right, so 2 divided into 1, or 1.0, and most of you knew this out there, gives us 0.5. All right, now 0.5 is what is called a terminating decimal because it stops, it ends. All right, so therefore these both are cases of rational numbers. Or I could take the fraction here, let me pick a positive fraction, and that should be a negative on that 0.5. Boy, watch your signs on these. I almost lost that one right there. Let me go ahead and pick the fraction 1/3. All right, so 1/3, if I made that into a decimal, if I divided the bottom number into the top number, 3 goes into 10 3 times. 1.0, okay, would be 10. I get 9, bring down the remainder, and what happens is I will keep getting 3 until I'm blue in the face. So this is what is called a repeating decimal, 0.3333333 forever. So 1/3 repeating decimal are rational numbers. All right, now there's some numbers on here we're still missing. Let me go back to the next graphic here. And I've also got some more examples of rational numbers there for you. Boy, we like to give you lots of examples here on the old BCC network. But there's some numbers like people that are kind of strange numbers, and they're irrational. You know how irrational people are. Irrational numbers do not end or do not repeat. All right, so an example of these numbers are listed here, and the one y'all might recognize more than some of the other ones. Notice some of them have the dot, 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 dots and go on forever. But the transcendental figure pi is an example of an irrational number. So let's go back and put that on the number line here. Let's go back and put pi on our number line. So now a lot of you know that pi is approximately equal to 3.14, but it keeps on going. It goes 3.14159 dot, 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 forever and ever. There was actually one of the colleges in the state that did a study on the number pi. Let me come up here to the camera and tell you this story real quick. There was a study done in 1980 on pi where one of the colleges in the state I think tried to take pi 1,000,000 decimal places to the right and never ever found a repeating pattern in it. I mean, they took and studied it for months and months. They looked at different areas of pi and so forth, but never ever found a repeating pattern. So it goes on forever, does not end, does not repeat. But when we look at our number line here, let's go back to it. We can put pi on the number line. We can say 3.14 or pi is about right there. Okay, so pi is on there. These irrational numbers are all on our number line. All right, so let's look at the next graphic here. The set of real numbers. All right, so the set of real numbers contains everything we've been discussing here. It contains the natural numbers, which you can see that set notation there is a subset of whole numbers, is a subset of integers, is a subset of rational numbers, is a subset of the real numbers. And even the irrational numbers are subsets of the real numbers. Okay. Now, I know some of you are looking at that saying, man, that's kind of strange there. But let me go ahead back to the example here and we'll show you something. All right. I'm going to give you guys out in the audience the number 4. All right. And is that a natural number? Well, sure, we could count 1, 2, 3, 4. All right. The caveman could count that. 4 is natural. Is it a whole number? Sure, it is a whole number. And if you look back at your graphics and notes there, you'll see that. Now, is it an integer? Sure. Is it rational? Can I make a fraction out of 4? Sure I can. Watch this. 4 over 1. Or could I make a decimal out of 4? 4.0. So yes, you can see that the natural numbers are part of the whole numbers, are part of the integers, and they're all rational numbers which lead into real numbers. So that's what that graphic was saying. And then those irrational ones are kind of the oddball ones. Those are the ones like pi that go on forever. They do not end and they do not repeat. All right, the next thing I want to talk about is some inequalities. Inequalities. All right, now inequalities contain these symbols. Now do y'all remember which one's which on these? All right. This is the less than symbol. Now, how do y'all remember that, the first one? Well, some people remember that the alligator mouth eats the larger number, or the arrow points toward the smaller number, or a high school teacher my wife had said this one looks like an L turned sideways. Do y'all see that? I don't know if I see that one or not, but yeah, you could stretch that and say it looks like an L turned sideways. So if you know this one's less, you know this one is greater. Now, the ones with the half of an equal sign in them, this one means less than or equal to. Okay, so it could be one or the other, and I bet you know what that makes this one then, huh? Sure, it makes this one greater than or equal to. Okay, now something to note on these inequalities, think about our number line. We just got done putting all of those numbers we use in algebra a lot on there. Any number to the left of the number line is always less than what? Any number to the right. All right, if you think about it, any number to the left is smaller than any number to the right. So we're going to do some examples here and see if we can get these connectors in the right spot here. -5 compared to -5, or 9. -5 compared to -9, excuse me. Would I put less in there? No. -5 would be greater than -9 because it is to the what? It's to the right on the number line. Negative 9 would be to the left. Or you could use the connector also greater than or equal to. Negative 5 is greater than or equal to negative 9. It's greater than. All right, next example, negative 9 versus 0. Now, were these in relation on the number line? Negative 9 is way over to the left of 0 on the integers. It would be less than. Or you could use the connector less than or equal to. All right, so now we're playing the inequality game. Let's play some true-false. True or false? 7 is less than or equal to 7. Well, it's not less than itself, but it is equal, so in this case we would write true. 7 is equal to 7, so that connector works. Over on this one though, check it out, negative 9 is greater than itself without that equal sign in here, and I wanted to show that's how these two are different. False. All right. How about 12 is greater than or equal to 10? Well, it's greater than, so yes, true. So on the ones with the equals to, it could be one or it could be the other. So make a note of how these symbols are different. All right. A couple ways to write inequalities. If A is less than B, then you could write B is greater than A as well. That makes sense. So in other words, if 3 is less than 5, well, doesn't it make sense then if one's smaller, the other one better be larger? Yeah. Or in the second example, I threw the equal to in there. If we have negative 6 is greater than or equal to negative 10, which is true, couldn't we also write then the reverse process? Well, if negative 6 is greater than or equal to, then negative 10 better be what? Less than or equal to negative 6. So that makes sense as well. All right, so a little discussion of inequalities. We're touching base. We will come back to these more as time goes on. The last topic of the day, absolute values. All right, the absolute value of a number is its distance from 0 on a number line. And they always use this symbol with the bars to show absolute value. So this symbol means the absolute value of x. So for example, what's the distance from negative 7 on the number line to 0? The absolute value of negative 7 would be 7. The absolute value of 3, the distance from 3 from 0 on the number line, 3. The fraction negative 3/4, its absolute value, its distance from 0 is 3/4. And the absolute value of this decimal point 0.07 from 0, it would be, well, 0.07. So do y'all see that when you take the absolute value of a number, it always comes out to be positive? All right, so in closing, now that you have the algebra concepts within your grasp, you know what to do. Math is like a bank. What you put in is what you can take out come test time. What you don't put in, you won't be able to take out. Think about it, take care, and we'll see you next time.